Well, hello there. Welcome back. Here we are talking a little bit today more about section 1.4, first order linear IVPs. Last time we mostly spent time talking about first order linear ODEs. And today we want to pick up where we ended last time, where we had the IVP, so we added the initial condition, right? And we adapted our general solution of the ODE to a solution formula for the initial value problem, right? The ODE plus the initial condition, okay? Now, our goal today is to make some remarks on existence and uniqueness associated with first order linear initial value problems, and contrast that a little bit with nonlinear ODE's initial value problems, like might appear in separable differential equations, which we know about. So anyway, so here we are. Let's just take a look at this solution. I've rewritten it. I tried to use, I think, the book's notation for it as well. Again, it doesn't, these dummy variables can be other things as long as they're not these guys, right? Anyway, I rewrote it like this, and so let's actually take this, since we just kind of wrote this down, let's do two things. Let's actually show that it is a solution of this initial value problem, right? Okay, so to show this guy, let's show that this y is a solution to the IVP. Well, what is that the same as? Show it's a solution. You show you have a solution. Which word up here on the board is kind of that? Demonstrate that you have a solution. That's the idea of existence, right? So we just plopped this guy down. Now we derived the general solution of our ODE. We'll kind of justify that terminology today. But you generally aren't just going to plug into this solution, right? This is for our theoretical benefit. If you're solving an initial value problem, you're going to use the process we used in the last video, which is put the ODE into standard form, find the integrating factor, multiply the equation, integrate, and come up with your solution based on the process of the way we did the solution formula last time and the example. But now what we want to do is say, all right, here's this guy, he's a solution to this initial value problem, so we're going to demonstrate existence. We're going to demonstrate that this solution that's sitting right here in front of us, so it exists, really is a solution of that. So what would we do? Let's do the easiest thing first. Let's look at the initial condition, right? So what if we evaluate y at x naught, right? If we evaluate this guy at x naught, that means we're going to put an x naught everywhere we see an x. And when we put an x naught right here, what do we get? E to the minus integral from x naught to x naught, 0, right? Good. E to the minus 0, we'll write it there so you see it, times what? I'm going to put an x naught, I'm going to evaluate this guy at x naught, that's what I'm doing, right? Integral from x naught to x naught, we just talked about, is 0, right? I was integrating this stuff, which depends on t, right? That whole thing becomes a 0, and then what's left? Plus y naught. Yay! What is e to the negative 0? E to the 0, which is 1, right? So what do I get? 1 times y naught, which is y naught. So yes, we satisfy the initial condition. Yes? Okay. So the initial condition is satisfied. Now we got to show that y satisfies the ODE. Ugh. Right, that's the hard part. Okay. We talked about, gave you last time, I said try it. Well, we'll see if you tried it or not, but you should try it now if you didn't, see what you get, and then you can just follow along, stop the video, and then come back and see how you do. So, what are we going to do? If we're going to show that y satisfies the ODE, we have to take its derivative, right? We have to take the derivative of this guy and see if we add p of x times y to it, that we just get g of x, right? So the goal is take this derivative. Okay, now what is this? This is a function of x. What is this solution? This piece is a function of x, and this piece is a function of x, right? Because of this guy, right? So I've got a function that I want to take a derivative of, and it's a product of two different functions of x. So what rule do I have to use to take that derivative? Yay, product rule, right? And so what does the product, you guys look so excited. What does the product rule say that we need to do, right? The product rule from calculus. So we're going to take y prime, right? So what is y prime as a function of x? Well, product rule says first guy, right? So we'll write that guy, first guy. So we're just going to rewrite that piece. Whoops, it's an S. Yeah, dummy variable. First guy times derivative of the second guy, right? Okay. So times, and I'll just write it like this, derivative with respect to x of the big bracket, right? Okay. What's in that bracket? Okay, I'll write it. X naught to x, right? E to the integral from x naught to t, p of s ds, right? G of t dt plus y naught. We're going to take the derivative with respect to x across that whole thing, right? That's a sum of two functions, so that's what rule? Calculus? Good, sum rule. All right, so right now we're just writing stuff out. So the first times the derivative of the second plus what? Right, the derivative of the first, okay? The derivative of the first, so derivative with respect to x of e to the minus integral of x naught p of s ds. We love this, this is so fun. Derivative of that, derivative of the first times the second. So I'm just going to put the big brackets there, and this time I'm not going to fill them in, right? Everything that's in that bracket goes in there. Yes? Okay, good. All right, so now what are we going to do? What do we have? Let's just kind of work this way, okay? So, well, no, let's work this way. Here we go. So this one's easy, right? We'll just try to go easy. Start with easy. We just write this down again, right? So what is y prime? It's e to the minus integral of x naught dx, p of s ds, right? Times the derivative. Oh, this derivative looks awful. Ooh, terrible, terrible, terrible derivative, right? How do I take the derivative of this? Okay, let's see. This is derivative with respect to x of this thing, right? Okay, for the first part of the sum rule. Derivative with respect to x of an integral from x naught to x of stuff of t dt. What is that derivative? Good. It's the fundamental theorem of calculus, right? What do? I write down this stuff that depended on t and replace the t with an x. Yes? Okay, good. So times the integral from x naught to x, times, what did we just say? E to the integral, so we write down the integrand, we're writing down the integral from x naught to, and I replace, oops, I need to write bigger, e to the integral from x naught to, we replace that t with an x, right? P of s ds, dummy variable, g of t, the t gets replaced with an x, good, right? That was the integrand in this guy, and I've taken that derivative now, right? Beautiful, fundamental theorem of calculus, awesome. Now, what does the sum rule say? Okay, so it's going to be plus the derivative with respect to x of y naught. What is the derivative with respect to x of y naught? 0, right? Y. What is y naught? A constant. Yay. Okay, good. All right. So that plus this. So now that we did that piece, that might make this a little bit easier. This is the derivative with respect to x of e to stuff, right? How do we take the derivative with respect to x of e to stuff? Good. E to the stuff, so we just write it back down again. Yeah? Times the derivative of the stuff, right? Now, if I'm going to take the derivative of this stuff, what am I going to get? I'm going to get a minus sign, right? Because I've got a minus out here, so I'm going to change this guy out here to a minus because it's multiplying. So that's the minus, taking the derivative of the stuff. And then it's a derivative of this integral, right? This is an awesome derivative again, right? Why? What am I doing? Taking derivative with respect to x of an integral from a constant to x of this integrand. So what do I get out of that? Loud and clear, loud and strong. We know it. What is the derivative of this integral with respect to x? Good. P of x, right? The integrand evaluated at x. Yes? Fundamental theorem of calculus. Okay. So we did the derivative of e to the stuff is e to the stuff times the derivative of the stuff. Yes? And all times that stuff, right? Everything that's in that big bracket that I'm not going to write out again. Okay? Okay? So, right, so stuff in bracket. Right? All of this stuff. Yes? Okay. Well, let's see what we can do here to simplify. What do we got? E to the minus integral of that thing times e to the integral of that thing. The exact same thing. So what is this times this? E to the 0, which is 1, right? Or that guy divided by that one, same thing, everything is 1. Yep. Awesome. So what do I get out of that piece? That times that? Beautiful. Just a g of x, right? And then I distribute this plus across my plus 0. I just get a 0 out of there. Well, that's looking kind of good. Okay. So what do I have? I've got g of x. Now I just need to look at that part. Gee, I'm just going to pull this p of x out here in the front. So it's going to be minus p of x. Yeah, minus p of x times this guy, e to the minus integral of x naught to x of p of s ds. Yeah, times that big bracket, right? Times that big bracket. That big bracket was this. You seeing it? That big bracket was this. Oh, what is multiplying that big bracket? E to the minus integral of that thing. So what is that part? What is this part right here equal to? That part is just exactly our guy y, right? So what do we have? G of x minus p of x times y. That's what this whole piece is. That part is all y. And so therefore, what did we just discover? Y prime for this y prime is g of x minus p of x times y. Where do I write this? Let me be over here. I guess I can erase this. Let's just come back up to the top. We already checked that the initial condition held. Let's come back up here. So for this y prime is, what did we discover? G of x minus p of x times y. Right? Do we satisfy the differential equation? Therefore, if I just bring the p of x across, put this in standard form, right? Y prime plus p of x times y is equal to g of x. Indeed. Woo! Yeah, right? What did we just do? We just demonstrated that this crazy function satisfies this initial value problem. We've demonstrated the existence of a solution. Like if this had been plopped down to you, we kind of saw where it came from, but we can pretend like it just got plopped down and, you know, you want to justify existence, it exists, right? It's sitting right here. It's going to exist as long as, right, well, we can, you know, do nice things like integrate these guys, right, and integrate that. And so what are you going to need, right? You're going to need continuity. That's what we usually require, right, with integration, at least at this stage. We're going to need continuity of these guys, p of x and g of x. They're going to need to be continuous, and then this solution is going to be nice and exist by powers of calculus. Yes, right? We're going to come back to that in just a sec. Okay, so we've justified existence, yeah? And we had some fun taking derivatives, yeah? Okay. So, the other thing is uniqueness. So let's look at how we generally, in mathematics, talk about a uniqueness argument. All of this is much, much more difficult for nonlinear equations. It's one of the reasons why we're talking about it with our linear IVP, okay? So let's now show uniqueness. We just justified existence. So what? What do you do? What does uniqueness mean? Okay, so existence means, well, there's at least one solution. And we just demonstrated it because we took derivatives and evaluated the initial condition and guaranteed that that guy is a solution. So a solution exists, but is it unique? Maybe there are other solutions out there that don't look like this for this initial value problem, okay? Maybe. We don't know. It would be super nice if this contained all possible solutions, yeah? And if there weren't, I mean, if this contained it, if this solution was it, yeah? There wasn't something else that could solve this initial value problem, right? So the question is this guy unique? Well, when you want to know if something's unique, you what we generally do is suppose there's two, right? So what does unique mean? There's only one, okay? We already have one, we now want one and only one. You suppose there's two, and then you try to show they're the same, right? That they would have to be the same, okay? So what's the simplest way to do that? We say, suppose there are two solutions to our initial value problem. So we got to give those solutions names. We'll just call them, since they're two solutions and they're both, expressions for y, we'll just say, call them y1 of x and y2 of x, okay? Now, we don't have to involve this guy at all, right? Okay, one of them could be this guy, because we know that's a solution. The question is there another one, right? But we don't want to even involve that messiness. We've already dealt with that. So, we have two solutions out there in the world, right? So let's consider their difference. How do they differ, right? Let's call that another letter, often v, right? So v of x is just the difference between y1 of x and y2 of x, okay? So that would be the difference between two solutions of this differential equation. Now, what do you think we want to be able to show the difference has to be? If we're going for unique, good. We want to somehow show that v has to be 0. That's our goal. If v has to be 0, then y1 has to be y2. Yeah? You have two solutions, they got to be the same. All right, so let's, sometimes we'll use this notation. Sometimes we'll just keep it shorter. V equals y1 minus y2, right? They're all just functions of x. Okay, so let's consider, since we know y1 and y2 both satisfy that differential equation, it makes sense for us to consider, well, what equation does v satisfy, right? So what happens if we look at that left-hand side and look at v prime plus p of x times v? Okay, so what would we get from v prime plus p of x times v? Okay, well, what is v? V is y1 minus y2, right? I'm just plugging in, not doing anything, plus p of x times y1 minus y2, right? I'm just dropping the of x because it's shorter, yeah? Okay, well, this is the difference law, lots of calculus laws, right, for derivatives. So this is the derivative of a difference is the, good, difference of the derivatives, right? Provided those derivatives exist. You know those derivatives exist because you knew that y1 and y2 solve this initial value problem, right? And so therefore the derivative had to exist. Okay, plus what? Distributive law, yeah, p of x times y1, distributive law, good, minus p of x times y2, yeah? So that's v prime plus p of x times v, yeah? Well, we could probably group this in a little bit nicer way. Anybody have any suggestions about what might be a better way to group this? Ooh. Hey, maybe we'll get the y1s, like, so maybe we'll write it as y1 prime plus p of x times y1, right? We'll get that guy there. And then we've got minus y2 prime minus p of x times y2. Are you getting excited? Do you see it? Okay. It's going to make my life a little bit simpler, right? So minus and a minus, I could put a minus out in front, factor it out, and then this becomes a plus. Yes, you guys agree? Woohoo, okay, super exciting, right? I'll even put parentheses around this guy because, you know, we're allowed to do that by laws of algebra, right? And so, tell me, what is y1 prime plus p of x times y1? What is that? What is it? Wait a minute, what was y1? y1 was the solution to the initial value problem. So if y1 solves this initial value problem, then what is y1 prime plus p of x times y1? Has to be g of x, right? It satisfies the initial value problem. So that is equal to g of x because y1 solves the ODE. Yeah? But what do we know about y2? Well, y2 solves the ODE. So what does y2 prime plus p of x times y2 have to be? Also this exact same g of x, right? This is also g of x, right? Why? Because y2 solves the ODE. But what is g of x minus g of x? 0. Beautiful. Awesome. Fantastic. Yes? Awesome. So what do we know about v prime plus p of x times v? V prime plus v try that again. So v prime plus p of x times v is equal to what? 0. Now, we wanted to show v was 0. We haven't gotten there yet. By considering that guy, okay, let's see. Does that equation look similar to you? Hey, wait a minute. This is an ODE. Classify it. Classify it while I create some more space here on the board. Yeah? Okay. What is it? What order? Is it separable? Is it autonomous? Is it homogeneous? Is it linear? Is it nonlinear? Good. It's first order, right? It's linear because what is our dependent variable? V, right? What is our dependent variable? V. What is our independent variable? X. Good. This is a differential equation for v as a function of x. So is this autonomous? No. P is some function of x, right? So it's not autonomous. It is linear. It is first order. It is homogeneous. And it is also separable. And it is one you saw before, okay? This is the same ODE as our integrating factor. Right? What do we got? We've really gotten it as the derivative of v with respect to x is equal to minus p of x times v. We can write it that way, right? So dv over v, we'll do this quick, is minus p of x dx. Yes? Okay, now what do? We integrate. X stuff on one side, x is the independent variable. This stuff depends on x. V is the dependent variable. V stuff on the other side. What do we get? Natural log, absolute value of v, you're getting so good at this by now, is equal to what? Well, we can't integrate that guy, right? Okay. So he's just the integral, right? Minus b of x dx, right? And then what do? Right? Exponentiate both sides, right? And when we do that, we get an absolute value, but then we get v as a function of x is some constant, e to the integral of minus b of x dx, right? Yeah, okay, there we are. Now, that was the ODE v satisfied, right? What initial condition does v satisfy? The IC for v is what? Well, we're going to evaluate v at x naught, right? But what was v? It was y1 minus y2, so that's y1 at x naught minus y2 at x naught. Yeah? But what's y1 at x naught? It's y naught. Why? Why not? Because y1 satisfies the initial value problem, right? So y1 at x naught has to be y naught. And what is y2 at x naught? Y naught. Why? Because y2 satisfies the initial value problem. So y2 at x naught has to be y naught. Yeah? Beautiful. And so what is y naught minus y naught? 0. So what does initial condition does v satisfy? V at x naught is 0, and now you're super excited, right? We came up with an ODE for v. We have this solution, but now we have to pair it with this initial condition, and you know this equation and this guy with an initial condition of this very well by now, right? If this guy is going to be 0, then what does that mean? Yes, c has to be 0, and therefore v of x is identically 0. Okay, 3 equals, right? Just to make it, right? V of x is identically 0, and therefore, once we apply the initial condition, and therefore what was v? y1 minus y2. So we supposed we had 2 solutions, and we showed that their difference was 0, or that if you have 2, they have to be the same. They're not really 2, they're the exact same thing. So that is super cool. And we are also going to talk a little bit more about how nonlinear problems relate in our theorem, our Picard theorem, but I am going to have to stop because I have another meeting. So let's just think about now, as we close out, maybe I'm going to erase this right here, okay? So we've got the uniqueness, we have shown existence and uniqueness. That's a classic type of uniqueness argument. It's a nice, simple argument when it works. Next time we're going to think about this guy in the framework of y prime equals f of x and y, okay? So what would f of x and y be for this guy, right? We would just bring our, we'd have minus b of x times y plus g of x. Oh, do I have time? Do I have time? No, I think I'll stop. So you should think about what does Picard say about this problem, and then we'll come back in another video and talk a little bit about comparing and contrasting nonlinear problems. And our nice linear problem where as long this is the unique solution, and as long as these integrations are possible, then we have a nice continuous function that comes out of it. So these guys, the continuity of these functions ends up being the only thing that determines where our solution of this initial value problem could have problems, right? It could have problems. Just think about this, right? What did we need for Picard? We needed f continuous, right? And partial f, partial y continuous, right? And what is partial f, partial y for this problem? Good. Minus p of x. Good. And what is f? This times y plus g of x, right? This expression is continuous for all y, and it could only be discontinuous where p of x or g of x are discontinuous. And so those, the coefficient function and the non-homogeneous right-hand side, where those have discontinuities, end up ruling the day for linear problems. And without those, if you have no troubles there, you know you have nice things happening, which may not be the case with nonlinear, but you'll have to wait for another video.